I'm a master's student at University of Mainz, and I'm going to show some of my work on finding the intrinsic resolution limits in the low energy regime in IceCube. So I'll give a brief introduction about IceCube. It has already been covered in today's morning's lectures. So this is IceCube. This is a cubic-kilometer neutrino detector at the South Pole. And these are our sensors which are embedded into the glacial ice. So these we call it the digital optical modules, or in part the DOMs. And these capture the Cherenkov light, which is given off by a charged particle when it travels through the ice. And these charged particles are produced when we have an incoming neutrino. It interacts with the ice and there's a charge current interaction. And so this is what a low energy event looks like. So this is a 25 GeV event. So these spheres represent the hit sensors. And from the positions of these hit sensors and the timestamps of the registered hits, you could infer about the direction that the charged particle travels through. Okay? And these two pieces of information usually goes into a reconstruction algorithm, and the reconstruction algorithm estimates the direction energy as one of the many parameters of interest of IceCube. Now, this is both challenging and interesting at the same time. I mean, it's challenging because we have just a few Cherenkov photons, because the number of Cherenkov photons emitted usually is proportional to the energy of the particle. And this of course leads to fewer hits, and it's very difficult to do reconstruction with just a few hits. This is interesting because working in the low energy regime has many promising prospects. For instance, it would promises to help us solve the neutrino mass hierarchy problem and set constraints on the oscillation parameters, and also a possible new tau identification, and into much more exotic stuff like the sterile neutrino detection in the future. And to tackle these challenges and to probe into the low energy regime, IceCube has an existing subarray. It's called the IceCube DeepCore, which has a vertical separation of 7 meters. This is the bird's view of IceCube. So the green strings, the green sensors are the IceCube DeepCore strings. And we have also planned on building a future, even denser subarray called the IceCube Upgrade, as shown in red, which has almost half the separation of the currently present IceCube DeepCore. And my work involves working with reconstruction in both of these geometries. However, I will just be showing the IceCube Upgrade results today. Okay, now towards my work. So I'm I'm interested in knowing the aspects which are limiting the reconstruction performance at lower energies, and usually the directional information of the charge of the second charged electron is smeared out by a transverse hadronic shower, which usually develops whenever neutrino interacts with the ice. The fact that photons scatter whenever they travel in ice, and also that our sensors have a limited detection efficiency. And finally, what I want to answer is what are the resolution limits if we have access to this Monte Carlo truth information. Now, towards the reconstruction, I have a twofold approach here. I am using the direction and the timing information of hit photons. And for this, I construct a loss function where I'm looking at the angle between the hit photons and the hypothesized charged particle direction, and then deducting the Cherenkov angle, which is 41 degrees. And what's happening here, to understand this, you can look at this cartoon here. So we can imagine the charged particle moving into the screen, which is shown by the red cross here, and the loss function goes to 0 for one photon, for each photon on the green circles. And so for an even, if there are a number of photons, we have a number of circles, and then the common intersection point gives you the global minimum. And this is a very simplified case. This is the case where there is no scattering. So we have a very well-defined minima, as you can see in the light landscape to the left there. But then the situation becomes a bit complicated when we have scattering, because when we have scattering, the photons deviate off the Cherenkov cone, and then you have circles which are overlapping in all possible ways. And in the light-colored landscape now, the dark region kind of diffuses out, and the minimizer gets lost somewhere in one of the local minima. And what happens here is that if you compare the resolutions in the no scattering case, it was very close to 0, and now it kind of degrades to around 16 degrees. And moving forward with this, we also have the timing information of photons now, and I follow the usual develop it in a similar way as I did with the direction information. And I won't go into the math here, but what I do here is look into the difference between the observed and the geometric timestamps, and do compute the geometric timestamp I just put a reference timestamp on the interaction vertex, then add the time that it takes for the photon to be emitted along a track, and then add the time it takes for the photons to travel to the sensors traveling through the ice. And then I proceed similarly as I do in the direction case, minimize the loss function, which gives me the optimized parameters. And then once you have the optimized parameters, you look at the angle between the opening angle between the truth and the optimized reconstructed vector, which gives you, which is shown in the y-axis here. And I want you to look at the green plot here, which includes both these hadronic shower spread as well as scattering. And you see that if you are only using the direction information in the lower head count range, the delta theta goes to 40 degrees. However, the timing information gives you a much better result at around 10 degrees better at 30 degrees. And I have another plot here shown in red here, and what I call this red plot the smearing of truth information. And it usually encodes the detector efficiencies, because what I do here is I have the truth information of the photons and I project it onto the PMP vector of the nearest PMP to the point of photon impact. And I also include the acceptance information of each sensor, which of each PMP, which simply tells you the probability that a photon which makes an impact would actually register a hit. And usually all the photons which come from along the axis of a PMP register a hit, whereas those which are orthogonal to it almost never do. Right? So you see that the resolution degrades further to by around 8 degrees in this direction plot here. Now, this process is really this is a good approach. It's also quite fast. It takes around 3 milliseconds for even more than 100 hits, but we are not sure if it does provide the optimal performance. And this solution here is to use a likelihood approach with a true underlying PDF. But there's a problem here. The problem is that we have a grid-like structure of arrays in IceCube, and so there's always a biased sampling of photons via sensors. And what it means is that the PDF just changes with the change in the interaction vertex position and the direction of your charged particle, because the particle just sees a different kind of a geometry around it for every given direction or position of the interaction vertex. And what you could do is you could track every single photon, which is computationally expensive, or what I do here is you randomize the geometry. So it kind of appears the same no matter from which direction or which position the interaction vertex is. And the result is quite promising. So this is for just different directions of a charged particle, and you see that there's a very good agreement within Poisson error limits. So now we can use one of these PDFs for all of your events, and you do not have to generate a new PDF every time, which saves much of your computational time. And once you know this, you have to model your PDF, and for this I use a kernel density estimation. And if you naively use a kernel density estimation, KDEs usually try to capture the bulk of your data and kind of misses out on other things, such as if you have a skewed data, skewed distribution like that, it often misses the tail, or even more sensitive areas like the peak here, which corresponds to the least scattered photons. And so what I do here is use a variable bandwidth approach. And in a variable bandwidth, you define a window which passes through your data set on each of your data points, and the bandwidth is calculated depending on the density of data points inside that window. So depends on the localized densities, and then you sum up all of those individual kernels up to give you a KDE, a nice beautiful KDE, as you can see here, and it agrees with the histogram bin populations within one quasar, which is really good. And once you do that, you usually do the reconstruction, and you do see an improvement over the earlier used loss function approach. So if you're only using the direction information here, you can already see. So the likelihood approach is shown bright red here, and the loss function is shown in brown here. And you already see an improvement of around 20% at lower hit counts, and there is a similar significant improvement if you are using the timing information here. Okay, now that we have used the direction only and timing only information, it would be interesting to see what a combined analysis gets us. And so I started off with usually just adding up the log likelihoods that you get from the direction only and timing only approach. So in short, you're just multiplying the PDFs that you get. And there was no significant improvement really. And the problem here is that we are not using the correlation between the timing offset and the direction offset, because we know that if the photon which travels for a longer period of time undergoes many more scatterings, and so the direction offset is somehow correlated to the timing offset. So the correct way of doing this would be to create a 2D histogram here, where each of these entries are the direction and the timing offsets for each of those photons. And then you do a 2D KDE fit using the formulation that I described a few minutes earlier. And then what you see here is that there is actually quite a lot of improvement. So in red here is using only the timing, only the direction information. In orange using only the timing. The brown one is using the naive summation that we were doing earlier. And now using the synergic effect, you see that there is a 40% improvement over the naive summation method that we were employing earlier. So this is really nice. And now, once we have that, we could do a comparison with the benchmark algorithms that we have on IceCube simulation. So this one is the one in red uses a graph neural network, and it's one of the best performing reconstruction algorithms on IceCube Upgrade simulations. And what you see here is that there could be a further improvement of 33% in the lower hit count range. But the interesting aspect of this plot is that it seems like at higher hit counts, the reconstruction is already using all of the available information. It doesn't seem to be a lot of improvement in the future now. Okay, and now towards this direction in the future, I plan on extending this work onto a DeepCore like geometry, because it would be interesting to see what kind of resolution improvements you get from the upgrade as compared to a DeepCore like case. And I'm currently also trying to improve the modeling of the PDF, because what I recently observed that if you just cut a slice in the 2D histogram, which is the Cherenkov angle area, you see that there is a bit of a disagreement with the histogram bin population and 3D estimates. So I'm currently working on that, and hopefully that will lead to an improvement here. And yeah, that's all from my side. I'm questions?
Do you have any? Sorry, do you have any specific analysis where you plan to use this method? I guess specific search.
Not that I have in mind right now.
Where do you think it will help the most? Like you're looking for galactic like sources, you're looking for extragalactic sources, you're looking for something else.
Means low energy, right? So
Yeah.
You sample.
I mean, it would probably lead to much more better constraints of the neutrino oscillation parameters, I would guess, because you are getting a better directional reconstruction, which gives you the path taken and so on. So that's, I think, that would be nice, actually.
Thanks.
Energies here are 10 gigaelectron.
This is between 1 and 20 gigaelectron.
Yeah. And if you can go back one slide. So maybe you just actually this one here actually, yeah. So I had a question, but you probably answered it. So the this white stripe that you show there, this is actually the Cherenkov angle. So
Yes.
0 would be the original direction of the muon.
Yes.
Okay,
And
then
the Cherenkov angle is,
yeah, and then you scatter off the Cherenkov angle.
Yes.
Okay. Okay, and I guess the reason why this is not symmetric is also like a phase space.
Yeah.
Like that. Okay.
Yeah.
Maybe to follow up on that question. So you just showed directional resolutions, but what about the energy, which is like via the so interesting for oscillation analysis?
Yes, that is another parameter which is interesting. My work actually started with energy reconstruction, but the amount of work just seems so huge that I instead just prefer to go in one direction, because it's very hard to do both energy and direction during a master's period. I think that's, but maybe if you're working on this in the future, I could continue this analysis and extend it to the energy here too. Yeah.
Okay, let's thank Kaustav again.